अगर आप AWS Azure क्लाउड यूज करते हैं और कॉस्ट एंड कॉम्प्लेक्सिटी से
Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be starting with the trie playlist. The trie is considered as one of the toughest data structures that is generally asked in an interview. But trust me, after you watch this entire playlist of trie, you will be like super duper confident about any question that is asked related to trie. Now we will be solving the first question today in order to understand what is trie, when it is used. So basically, trie data structure is used whenever you have something like they're saying, hey, insert word. That means store this particular word. Then they're asking you, does search word, does this word exist with you or not? Then starts with word. Is there any word whose prefix is this particular word? So these are the functionalities that trie generally helps us to implement, and we're going to learn about that in today's lecture. So let's take a quick example. So over here you see there is hello. They're saying one hello means can you please insert hello? That means store that hello into your set of words. Next is help. Can you please store help into your set of words? Next they're saying to help. To means does there exist any word as help? You'll be like, yes, there does exist because we already inserted one help. The next one is, does there exist any word which starts with HEL? Starts with, very important. Three means starts with. Is there a prefix HEL among all the words? There are. This has a hell as prefix. HEL is again a prefix over here. So there is a minimum of one word. So true again. To HEL. Does there exist a word with HEL? No, because there are two words as hello and HELP. So there does not exist a word with HEL. So you return a false. So this is what we have to implement. And for this, we are going to use the data structure, which is known as trie data structure. Now, what is a trie data structure? In order to understand this, let's take some example. Assume I am asking you to first insert. Let's first understand the insert functionality in trie, and then we will understand the rest too, which is starts and prefix functionality. So for insert function, we have to understand what is a trie data structure. So in order to understand insert, what we will do is we will take some words. Let's assume I take apple as one of the words, then I take apps as one of the words, then I take something like APXL, then I take BAC, then I take BAT. So these are the 5 words that we will take in order to understand the insert functionality of the trie data structure. Now, what is a trie data structure? Let's first understand the structure of trie data structure. Generically, the trie data structure is a class or a struct if you're using C++. In C++, you can also use a class. So trie data structure is a struct or a class, and they have two member functions or two variables to say. Now, assuming that all the characters are lowercase, what I will do is I will say int. You can take this as anything, and the array of size 26, and there will be a boolean flag which will be false. So this is how the trie looks like it's a class, struct, whatever you can call it. It has a array of size 26 and it has a boolean flag. Okay, now there will always be a root. Now this is what is called as the root of the trie data structure. Now initially the root will be having, like, this is a trie. Now whenever I say trie, I mean that it has an array of size 26 and it has a boolean flag. Okay, so this is a trie. That means it has an array of size 26 and it has a flag. So I can say let's mark flag over here. For this, flag is false. So let's mark flag as false. Now it has an array of 26, but as of now I'm not marking it. So assume this as the 26 size. Assume this as 26 size. I'm not marking it. We'll just mark whatever is required. Now let's come across and try to insert the first word, which is apple. Now whenever we are saying insert apple, what you do is you start with the root. Yes, you start with the root and you ask the root. Now remember, whenever I say 26, 0 means A, 1 means B, 2 means C, but this is how I'll be calling up the indexing. So whenever I say, hey, for apple, what you're starting at the root. You're starting at the root. What is the first alphabet? A. The first alphabet is A. Now you're going to ask, hey, listen, does A exist in your root? They'll be like, no, all 26 are as of now empty, because whenever you just declare, that means it is empty. All 26 are empty. So you'll be like, okay, hey, listen, can you please go to the index 0 and insert A? I'll be like, okay. Now whenever you insert A, just make sure for A you create another try node. So A will be pointing to that try node. Just make sure you create that. Now another try, what does that signify? Whenever I say another try, that means with the flag as false and again 26. Okay. Now you have done with A. You're done with A. Now A is pointing to this. Okay. So for A, this is what you mean. So A is pointing to this try. Now whenever you come to P, now in order to come to P, what you'll do is you'll come to A's reference try. So you have come up to A's reference try. Now what's the next one? P. Now you'll ask this guy, does P exist? I don't see, because it's a null. So what you will do is you will simply take a P, yes, and again you'll create a P's reference try. So please create a P's reference try. Again you can create the P's reference try, and then P will be done. What's the next alphabet? Again P. So you're currently standing at P. So which is P's reference try? This one. You'll come to here, and now you'll ask, does there exist a P? Because the next alphabet is P. No. So again you'll insert a P and you'll create a P's reference try. So let's create a P's reference try.
Stop. Before you buy this. This exact product could
Created. What's the next reference try? Here, and you will insert it reference at E. So when you come to E, where are you? You are at else reference. So what you'll do is you will create E and you'll create E's reference try. Initially the flag will be false, because for E, when you create the reference try, this is how the try will be created. So A of 26, which is this, and then boolean flag equal to false. This is how it is created. But remember, whenever you come to E is completed, which means the word has been completely traversed. So it's completely completed. Now, since it is completely completed, what is the last reference that you're standing at? This try is the last reference where you're standing at. So since the word is already completed, you'll be like, hey flag, can you mark yourself as true? You'll be like, okay, let me mark myself as true. So let's mark himself as true and keep it. So this true signifies that E, this try, there is a word that ends with this particular E. Got this? Perfect. Now what we will do is, we'll come to the next one, that is apps. When I come to the next word, that is apps, for this A, we will be standing at root and we'll ask, does there exist an A? He says, yes, there exists an A. So our pointer will move to the reference try of A. So we are now over here. Okay. Next, does there exist a P? Yes, there exists. So you'll now move to the reference try of P. We will be standing here. Does there exist another P? Yes, there exists. So you'll move to the reference try of P. So you'll be standing here when we are at S. Okay. Whenever we are at S, we will be standing here. Does there exist an S? No, because there is an L, but there is no S. There is no S. So what you will do is, you will say, okay, since there is no S, let's create an S and its reference try. I'll create a reference try for this and I'll keep the flag as false initially, because I'm creating a reference try. So initially it will always be false. Going forward, I can say, what's the next? The next is nothing but very simple. If I'm done with S, that means the word is complete. The word has been complete. If the word is complete, you know, wherever the last reference try is pointing, which is this, you'll just go over there and you'll say, hey, listen, can I do the flag to be true because a particular word? So that is how you insert. Okay. Next, APXL. So let's again do the same thing. You'll initially, do you have a P? You have this reference, you don't have an X. Try. Created a reference try. So A, P, put an L, and again. Next, already in last reference, XL. Very simple. For apps, APPS, it is over here. So you can easily find this out. So it's very simple. Now for BSC, for the next one, whenever I come to BAC, how will that get inserted? On the root, do we have a B? No. Insert B. Create a reference try and make flag equal to false. Do you have an A? No. Create an A. Create the reference try and make flag equal to false. Do you have a C? No. Create a C. Create a reference try and make flag equal to false. Now the moment C is over, the moment the word is over, just go back and the last reference wherever you're standing, make next. Yes, be over here. For create a T relatively false, and once it is completed, you can go back and make it true. So this is how you can store the entire try data structure. Quite simple. Remember just one thing: for A, this is the reference node. For P, this is the reference node. Remember, reference node concept is very important because A is defined by this reference node and this is the starting point. This is just the starting point. This is how the try data structure is created. So that is about the insert function. Now we will be learning about the search functionality. So that was about the insert functionality. Now we will be learning something which is known as the search functionality. Can you just tell me if a word like APPS exists or not? Can you tell me if a word like APPL exists or not? How will you basically implement that? It's very simple. If you have this entire structure created, the moment created, yes, if you have this entire try data structure created, the moment someone says, do you have APPS? You always stand at the root and you start. You look for the first variable A. Does there exist an A? So the reference variable is here. Yes, there exists. Does there exist a P? The reference variable is here. Does there exist another P? Yes, the reference variable is here. Does there exist another S? Yes, the reference variable is here. Right? So at the end you're standing here. Is it over? Yes, it is over. Is it true? Yes.
Albion has people that just log in to play the market, and honestly, I kind of respect it. See, that's the thing about Albion Online's economy. You'll see people who...
So the last reference where you're standing, it is true, which means there does exist a word. I will repeat. APPS. You start this one. Does P exist? Yes, P exists. Reference variable, this one. Does P exist? Yes. The reference variable. This is over. Over. Once it is over, the last reference where this particular word does exist. Does A exist? Yes. This one. Does exist? Yes. Reference. And if APPL is completed, you're standing over here. This is the last reference node where you're standing at, because for L, this is the reference node and this is where you're standing. Is the flag marked as true? No. The flag is marked as false, which signifies there is no word that ends with APPL. There is no word that ends with APPL. As simple as that. So that is how you implement the search functionality. Now we will be doing something as starts with. That means, does there exist any word that starts with BA? There does exist two words that starts with BA. Does there exist any word that starts with APD? I don't see, because there is APP, APP, APX, but nothing as APD. Like no word starts with APD. That is what the question is all about. Let's check out if there exists any word that starts with BA. How are you going to do this? As usual, you'll be standing at the root. First letter B. Does there exist a B? Yes. Reference, this one. Does there exist a A? Yes. Reference, this one. This is over. Now at the end, if your not standing at a null. It's very important. At the end, if you are standing at a try, that means there was a possible prefix. Otherwise, you would not have been standing over here. If there was nothing, you never would have been standing at a try. So if you're standing at a try, that means there was a BA. There was a BA. Yeah, the longer word can be anything, but there is definitely a BA. That's why you started with B. For B, this was the reference. For A, this is the reference. So for B, for A, you found a reference. That's why you're standing over here. So thereby, if I'm standing at a not null position, if I'm standing at a not null position, I can say this. There are words that starts with BA. Let's check out for APD. A, yes. For this is the reference. P, reference. D. Does there exist a D? I don't see a D over here. Do I? No. Thereby, this will be pointing to some null. So the moment you try to access D, you will get null. So if you are encountering a null at any of these instances, and you're not encountering a try, like A. For A, you got. For P, you got. But for D, you did not get anything. Thereby, you can say there does not exist any word that starts with A, P, D. Because for A, you got. For P, you got. For D, you did not get any reference try. Thereby, D does not exist, which means there is no word that starts with A, P, D. So this is how a try data structure can be easily implemented. So I hope you have understood the insert, the search, and the starts with. So remember, I will be coding the insert, the search, and starts with right from scratch. So nothing to worry about. Let us code, and the moment I will be coding this, it will get much more clear to you as I move across. So let's start coding. Code that I will be writing will be industry standard. So I'll be maintaining class, functions, and everything. There's nothing to worry. You can just follow me and you'll learn the entire stuff. So what we are given is basically a class. By the way, the C++ code is on the left, and the Java code I have pre-written because I cannot write both the codes together. So for Java people, they can just follow me when I write the C++ code, and they can just look at the transformation into Java on the right hand side. But you can follow it because the syntax is almost identical, because I'm just going to use for loop and arrays, so that doesn't matter, right? So initially you're given the class try, and then there's a method constructor, and then they're given insert. So there's a functionality of insert as we discussed. Then there is something as search, when they say that, okay, take this word and tell us if it exists or not. And then there is something like boolean starts with. Does there exist a word that starts with this particular prefix? Okay, so what I will do is, as I said you, that there will always be a struct node. So let's write the struct node, right? And what did I say you? There will always be a reference node. Now, my pardon, when I was discussing, I wrote int, but there will always be a node star, and you can probably keep it as links, because for every character, there will be a reference link. So assuming all are lowercase, I'll keep it as link 26. Now then I'll keep boolean flag equal to false. Initially, that's what I'll keep. That is what I have initially kept. Now, we have a try, right? What are the stuffs that we require? We require one stuff which tells me does there exist that stuff or not, but we'll come to that afterwards. Now assume that this is the initial stuff of struct we have. Now we are having a try. So in try, what's the first thing that we require? We definitely require the root. So I can just define the root, because initially every try will have a root. So I've declared that. And after this, what I'll do is I'll say root equal to, yes, root equal to new of node. So whenever this constructor, like whenever the class's object is created, we will create a root of new node, which basically signifies that, hey, listen, we have, this is absolutely a new object for this particular class itself. Okay, this is what we will always have. Anytime anyone creates a constructor, he'll get a new try for himself. Okay, after this, we have an insert of word. So if you remember, while inserting, we always started with the root. So let's create a node star node equal to root. So this is basically a dummy variable node, which is initially pointing to the root. That is what we have started with. Now we need to insert every character. So let's just move across what dot size or length, whatever you want to take. Now, what do we want to see? word I, because we need to check if the character, what's the character? The character is word I. Does that exist in your try or not? So for that, what I'll do is, I'll just create a function bool contains key. Yes, bool contains key. I'll pass him the character. He will say me yes. If the link, because this is what it means, links. If the links of ch minus a, because I said a is 0, b is 1, c is 2. So if this is not equal to null, then you'll be like, hey, listen, that means it does exist. That means this character does exist. So while inserting, it's very important. If currently I'm standing at this node, which is the root, if node contains key, because this node, this is the reference try that I'm standing at, and I'm calling the contains key for this, and I'm passing the character as word I. Does it contain the word I? If it does, for this node, this is the while inserting, it's very important. If currently I'm standing at this node, which is the root, if node contains key, because this node, this is the reference try that I'm standing at, and I'm calling the contains key for this, and I'm passing the character as word I. Does it contain the word I? If it does not, then what I will do is, okay, you don't contain, so you have to keep it with you. You have to keep it. So what I will do is, I'll again create a function which is nothing but void put, where I say, hey, listen, this is the character ch. Yes, this is the character ch, and this is the new node that you have to put it across. So what I'm saying is, okay, that is perfect. So on links, yes, on links, that is ch minus a, can you say for this guy, the reference node is this? So basically I'm saying this is the new character, and for this, this is the reference node that I'm saying. So assume when you started with Apple, you'll pass a reference node that I'm saying. So assume when you started with Apple, you'll pass a, and you'll pass a new try for that. So Apple's a will be pointing to new try. That is what this put will do. Okay. So what I'll do is, I'll say, if it does not, yes, if it does not, then I'll call node and I'll say put. Can you put this Apple, like word I, with a new reference node, new try? So just make sure you put this new try. So once you have put this, now Apple has been put, like a has been put of Apple. Now can you just go to that? So you'll say node, can you go to the next one? So in order to get the next one, what you can do is, probably we can write something as get function, because something like node or void get, something like node star get, I'll be like character ch, and it'll be like return, where is this pointing to? Links ch minus a. Ch minus a is where it is pointing to. So what I've done is, I've put across. So I'm currently standing at the root. Remember, you're currently standing at the root, and at the root you have put across. But now you have to move to the reference try. So you say, hey, can you just move to the reference of this word? I just move to the new try. So this moves to the reference try. Moves to the reference try. So this is going to happen every time. Yes, this is going to happen every time, because this is how you create the new reference node, and this is how you move. So you move to the new reference try. Now once you move to the new reference try, you will insert. Again, you will come across and you'll see in the new reference try is the word I exist. If it does not exist, again create new, keep on going. And once this ends, once the entire word ends, can I say this node will be standing at the last reference try? And if it's standing at the last reference try, can you say set end, something like this, where you say, can you please set the end? So probably I can also write boolean set end, where I say, okay, the flag will be turned to false. True. So basically this was the last reference node, and it's a set end. So it'll go to the set end and say, okay, for this node, can you just turn the flag to be true? So at the last you will turn the flag to be true, stating there is a word that exists. Now this is as simple as it gets. The complexity will be simply bgo of length of the word is the complexity for insert, is bgo of the length of the word. Perfect. We have done the insert.
If AI is killing jobs, then why are forward deployed engineer job posting up 729%?
Will be industry standard. So I'll be maintaining class function. This is the reference. How are you going to do this? There, and you're not encountering a try stuff. So what we are given is basically a
What will I learn for 9 rupees?
Number one thing that you're going to get at 9 rupees is you're going
method constructor, and then they're given insert. So there's a functionality of insert as we, and there's a reference node. Reference. Now then I'll keep boolean flag equal to false. Initially, that's what I'll keep. Keep. That is what I have initially kept. Now in we have a try, right? What are the stuffs that we require? We require one stuff which tells me does there exist that stuff or not, but we'll come to that afterwards. Now assume that this is the initial stuff of struct we require. We this what I'll do is I'll I'll say root equal to, yes, root equal to new of node. So whenever this constructor, like when whenever the class's object is created, we will create a root of new node, which basically signifies that, hey, listen, we have this is absolutely a new object for this particular class itself. Okay, this is what we will always have. Anytime anyone creates a constructor, he'll get a new try for himself. Okay, after this we have an insert of word. So if you remember, while inserting we always started with the root. So let's create a node star node equal to root. So this is basically a dummy variable node which is initially pointing to the root. That is what we have started with. Now we need to insert every character. So let's just move across word dot size or length, whatever you want to take. Now what do we want to see? Word I, because we need to check if the character, what's the character? The character is word I. Does that exist in your try or not? So for that, what I'll do is I'll just create a function will contains key. Yes, bull contains key. I'll pass him the character. He will say me yes. If the link, because this is what the it means links. If the links of ch minus a, because I said a is 0, b is 1, c is 2. So if this is not equal to null, then you'll be like, hey, listen, that means it does exist. That means this character does exist. So while inserting, while inserting, it's very important. If currently I'm standing at this node, which is the root, if node contains key, because this node I'm passing the character, then what I will do is, okay, you don't contain, so you have to keep it with you. You have to keep it. So what I will do is, I'll again create a function which is nothing but void put, where I say, hey, listen, this is the character ch, yes, this is the character ch, and this is the new node that you have to put it across. So what I'm saying is, okay, that is perfect. So on links, yes, on links, that is ch minus a, can you say for this guy, the reference node is this? So basically I'm saying this is the new character, and for this is the reference node that I'm saying. So assume when you started with apple, you'll pass a and you'll pass a new try for that. So apple's a will be pointing to new try. That is what this put will do. Okay. So what I'll do is, I'll say, if it does not, yes, if it does not, then I'll call node and new reference node, new try. Has been put, like a has been put of Apple. Now, can you just go to that? So you'll say node. Can you go to the next one? So in order to get the next one, what you can do is probably we can write something as get function, because something like node or void get, something like node star get, I'll be like character ch, and it'll be like return, where is this pointing to? Link ch minus a.
Quant. Do you aspire to lead quant teams of international?
Ch minus a is where it is pointing to. So what I've done is I've put across. So I'm currently standing at the root. Remember, you're currently standing at the root, and at the root you have put across. But now you have to move to the reference try. So you say, hey, can you just move to the reference of this word? I just move to the new try. Try. So this moves to the reference try. Moves to the reference try. So this is going to happen every time. Yes, this is going to happen every time, because this is how you create the new reference node, and this is how you move. So you move to the new reference try. Now once you move to the new reference try, you will insert. Again, you will come across and you'll see in the new reference try is the word I exist. If it does not exist, again create new. Keep on going, keep on going. And once this ends, once the entire word ends, can I say this node will be standing at the last reference try? And if it's standing at the last reference try, can you say set end, something like this, where you say, can you please set the end? So probably I can also write boolean set end, where I say, okay, the flag will be turned to false, true. So basically this was the last reference node, and it's a set end. So it'll go to the set end and say, okay, for this node, can you just turn the flag to be true? So at the last, you will turn the flag to be true, stating there is a word that exists. Now this is as simple as it gets. The complexity will be BGO of simply B. BGO length of the word is the complexity for insert is the insert start with the root node. So yeah, I'll keep it like this: 0 to again. You're standing at node. You're standing at the starting point. That's tree. Now you will be looking for word I. Does it exist? Now how will you do that? If node contains, because you will call contains again. Remember, why am I writing these functions? So that I can reuse them. I don't have to write it again and again. This is what you call production level code. Remember, these kind of codes you should write in an interview. Then they will be like super happy. Does it contains word I? If it does not contains, in case it does not contains, then there is a problem. And if it does not contains, that means the word does not exist. So can you please return it? And if it contains, why don't you get me that? Yes, why don't you get me that? Something like node get.
On Domino's checkout. Coupon expired. Invalid coupon.
Just make sure you get me that. If it does not contains word I, that means it does not exist, or else you just get me that and you move across. So once you're like going to the reference, going to the reference, going to the reference. At the end, how can you determine? Yes, at the end, how can you determine if this node is a word? Like you have found a word. It's very simple. The last flag has to be true. So probably you can write a function as boolean is end, and you can return the flag's value. So can I say at the end, if I say at this reference is end, if that's equal to true, I can say return, or you can simply return the node is end's value. Without complicating things, you can just return this node it is end's value. Then you will easily get to know if there is a word that exists. Like you go across, and the last reference where you end, if that is end is true or not, you just simply say it. What about starts with? Like how are you going to implement it? So I'll keep the Java code as usual on the right so that you can just follow me. Now, how are you going to implement it? As usual, you're going to start off with very simple at the root. So let's start off with the root, which is definitely word.length. If it does not exist, it is false. There is nothing to do. And if it does exist, just move to the next. Then you move to the next. And at the end, do you need to check for a true? No. If you have reached to a reference try, that means this can be a prefix. So there is no need to check for end. You can direct. If you write this code, for this search the complexity code. For that reason, what I've given all the code links in the test, not as how did I code? Use coding where they write these lines, create a readable code that's readable in the interview. Then only the interview will be super impressed, and trust me, they will not get a chance to reject you. So, guys, I hope you have understood. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So this is the 5th lecture of the try playlist, and till now we have done problems where we have solved everything that is related to strings. We have checked for existence of strings, number of existence of strings, checked if prefix exists or not. Now we will be moving to the other type of problems that might be asked in the interviews, that is related to bit manipulation. Yes, so in order to understand this portion of the playlist, you should have a decent knowledge of bit manipulation. Just in case you do not have, you can watch this lecture. I'll be leaving the link out in the description, so you should have a decent knowledge about bit manipulation, and after that we can get started. So going forward, the next set of videos will be completely on bit manipulation. Thereby it's highly recommended you know bit manipulation. So today's problem that we will be solving is maximum XOR. Now what does this problem state? The problem states that you're given two arrays of non-negative integers. Very important. All the positive integers are given, and two arrays are array 1 and array 2. Now your task is to find the maximum value of A XOR B, where A is an element from array 1 and B is an element from array 2. That means you can pick a single element from array 1 and you can pick any other element from array B from two different arrays, and both their XORs should be maximum. That is what you need to do. For an example, they are given two test cases, and this is the first test case. Okay, so the first array is something like 6 and 8, where the second array is of size 3, which is 7, 8, 2. So you are given two arrays. You have to pick one element from this. So assume you pick 8 and assume you pick 7. So 8 XOR 7 will give you 15. So if you try out all the pairs from both the arrays, you will see 8 XOR 7 will only give you the maximum XOR, that is 15, and that is what the question tells you to return. So in order to solve the problem that we saw right now, we have to solve an easier version of that, which is given an array of numbers. So you'll be given an array of numbers and a particular number x. You have to find the max value of array of I XOR x. Now remember, if you understand this problem by heart, like if you understand it conceptually, then you can solve any problem related to XOR in tries. So you have to make sure you understand this particular problem. Okay. Whenever you're inserting all the numbers into the try, insert them in terms of binary bits. Okay, now we'll talk about that as we move across. What's the next thing that you will do? Once you have inserted all the numbers into the try, you take x and find the max number from the try, because the try contains all the array integers in terms of binary. Now you take x and find the max number from array where that number XOR x is maximum or maxima, whatever you can call it. So these are the couple of steps that we will be following. So let's first understand inserting all the numbers into the try, and then we will come across to the second part. Now before moving into the try section, let's understand how we will store numbers. We won't be like, if you are given 9, you will not be storing 9. Instead of 9, if you know what is 9, it's an integer. Assume it's an integer. This is the entire thing. Yes, just think it as a string. If you remember all the try previous problems, think it as a string. You will store it as a string, like 0, 0, 0, 1, double 0, 1. In a try, we are going to store it like this. Okay, now since it's very tough to draw such a huge try of size 32, because there will be 32 bits, what we will be solving is, in order to make it easier to explain, I have assumed that it's just like 0, 1, double 0, 1, which is nothing but 5 bits. So I'll explain you the problem in terms of 5 bits so that the diagram is compact, and while coding it, I'll turn it to 32 bits. Okay. Now, whenever I say a number, what will it have in binary? Either a 0 or a 1. Now, what should our try node have? Our try node should have a couple of links where the 0 is for the 0 and first index is for 1. Like, I think if we take a node in the try which has 2 nodes, I think our job should be done. Okay, now let's understand how do you insert. So first, let's assume the array contains numbers like 9, 8, 7, 5, and 4. Let's assume these are the numbers that the trie contains. So initially you will always have the root of the trie rather. And what will the root of the trie have? It will have nothing, because logically, if I speak, the root of the trie is having couple of guys. So 0, 0 and 1, and this is the root of the trie. Okay, so as of now 0 and 1 doesn't have any reference pointer if you remember tries. So let's take the first one, 9, and we'll be solving everything in terms of what? In terms of binary, 5 bits. So what is 9? So if I write it 9 is 0 1 0 0 1. Remove the insertion should be done in this fashion, like right from the left to the right. So which is the first one? It's a 0. In the root, do we have a zeros reference pointer? No. So what you'll do is, you will create a reference pointer for 0. Please create a reference pointer for the 0. So this one is done. Yes, this one is done. Now, what you'll do is, from 0 you'll move to this reference trie.
Still thinking DevOps is just for experienced engineers? Well, here's the reality. Companies today need engineers who can build, scale, deploy, and automate applications.
Moved. Now you'll be standing at this particular 1. Do you have a 1? Do you have a 1 reference pointer? No. So please make a reference pointer to this particular guy, which is 1. So you've made that. Next, you will move to the reference pointer and you'll stand here. For this one, you'll move here and stand. So this one is also done. Let's move to the next, which is 0. Do you have a 0? No. Create a reference pointer and have a trie to it and move to that particular trie. So this is also done. Next, you'll have this 0. Do you have a 0? No. Have that 0 and have a new trie to it. Perfect. This is also done. So you'll be standing here. Next, this is the 1. Yes, this is the 1. So insert it and have a reference trie to it. Have a reference trie to it. So if you carefully observe, you have completed the entire insertion of 9. Yes, you have completed the entire insertion of 9. This is 0's reference trie. This is this 1's reference trie. This is the 0's reference trie. This is this 0's reference trie. This is this 1's reference trie. So I can say 0, 1, 0, 0, 1. So this is what you have inserted, which is ultimately 9. So I have successfully inserted 9. Now it's time to take the next element and try to insert it. So the next element, that is 8. So let's try inserting 8. Again, 5 bits. 0, 1, 0, 0 is what 8 is. So you'll try inserting 8. Now if I ask you, does 0 exist? The answer to that will be yes. 0's reference trie is this, so 0 exists. So kindly have it ticked and you're standing over here, which is this reference trie. Does 1 exist? Yes, it does exist. 1's reference trie is this, so now you'll be standing over here. And 1 is also done. Next, does 0 exist? Yes, 0 exists, so you'll be standing over here. So this is where you stand. This 0 is also done. Next, does this 0 exist? Yes, there is a 0 which exists. Now does this 0 exist? No. A 1 exists, but not a 0. So what you'll do is, you will insert a 0 and you'll create a reference trie for the 0. Perfect. So this is inserted. So what I can say is, I have successfully inserted 8. And if you carefully observe, 0, 1, 0, 0, and then it's a 0. Since 9 was 0, 1, 0, 0, 1, it was only differentiated on the last bit. If you carefully see, in the last there is a 1 and there's a 0. Apart from this, entire trie remains the same because it is similar on this aspect. Thereby this portion is indeed similar because it's similar in this aspect and it only changes in the last arena. Okay, so we have inserted 8 successfully. Let's try to insert 7. What is 7? 5 bits again. 0, 0. Let's go to the... No, it does. Does this one exist? No. No. insert it, have a reference try created. So if you see 0, 0, 1, 1, 1 has also been inserted. So this is also inserted. Perfect. So if you carefully see, 7 is very simple, like 0, 0, 1, like you start from this 0, then you take this 0, 1, 1, 1. So this is how 7 will look like. Do you see? Try storing it. Next, 5. Let's write 5. It's 0, 0, 1, 0, 1. That is what 5 is. Let's see. Does 0 exist? Yes. Does 0 again exist? Yes. Yes. Of maximizing XOR so that the logic gets clear. Maximizing XOR. Let's understand this particular intuition. Whenever I say maximizing XOR, what do you want? X is given as 8. You want someone from the array. Like if you do a XOR with that guy, it should give a value something which is as high as possible. That is your concern, right? So what is 8? 8 is 0, 1. I'm talking about 5 bits because as of now we're solving the problem in terms of 5 bits. Then we can expand that to 32 bits. So 8 is this. In order to have a number, array of I, such that this guy, like XOR, this guy should be as big as possible. What do you want? You know that a number is formed by powers of 2s. Like this is 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. You want this bit because you know you're going to create a 5-bit number. You want this bit to be set. If not, you want this bit to be set. If not, you want this bit to be set. Because if you are able to set the bits from the left, the number will be more. Remember the prerequisites class? The number will be more. So ideally, in case of this 0, you want a 1. Correct? So that if you do a XOR, it gives you a 1. In case of this one, you want a 0. Because if it's a 0, you get a 1. In case of this 0, you want a 1. Because you'll get easily 1. In case of this 0, you want a 1. So that you get a 1. In case of this 0, you want a 1. So that you get a 1. So you get all 1s. Hence the number is the largest, which is around I think 31. The number is 31 or 63. Jo bhi hoga. Dekh lena. 63 hoga shayad. Whatever it is. You can see across. Let's check it out. Kitna hi hoga. 1, 2, 3, 3, 4, 7, 8, 15, 15, 16, 31 hoga. Yeah, it's 31. So it's the largest. So what do you observe? What is the intuition? It was for every bit. If you took the opposite bit, if there exists. If you took the opposite bit, then this guy would be 1. And if it is 1, then the number will grow. That's my entire intuition behind solving this particular problem. So if I write down all the array elements that I did take in this example in terms of binary, this is what we have. Then we have x as 8, which is 0, 1, 0, 0. Okay. Now what I want is, I'll hypothetically what I'll do is, in order to maximize this particular number on XOR, I'll try to start from the leftmost bit, like logically. I'll say for the 0, does any number have a 1? No. So I'm helpless. I cannot take any number that has a 1. So I'm bound to take 0 over here. Okay, perfect. Next I'll go over here. What do I have? I have a 1. I need a 0 over here. And this will give me 9. So the 9 option will go. Can I take 5? Yes. Can options open. I don't have 9 anymore with me. I just have 7. I take that guy. Now I again have a 0. So what's my logic? Because this 0, if I get a 1. So I see this gives me a 1. This gives me a 1. Let's go ahead and see. Again a 1 to make this 1. Correct? So I see that. Okay. So these options get eliminated because they give me zeros over here. I have a 0. Can I put a 0 over here? No, because I want a 1. That's the best thing that I can do. Do I have a 1? Yes. So I put a 1. Yes, so I put a 1. Now if I'm putting a 1, yes, if I'm putting a 1, what I get is, I get a 1 and this is the maximum I get, that's 15. So you saw the intuition, what I was doing. I tried to eliminate numbers. And I tried to do it bitwise. And this is what we will do using try. Now a question might arise in your head that, hey Striver, what if this guy did not have a 1? Then you had no other option, you had to take a 0. And if you practically see, you'll always eliminate numbers in this way that you get the correct number. You can try out a lot of examples. If this one did not exist over here, you would have taken a 0. And then there would have been some other example or something like that. Like you can take multiple examples and you can see that this actually works. And this kind of elimination, if you do it linearly, is going to take a lot of time. This is where we will involve try. Okay, so what is the number? The number is 8. Let's write it in terms of bits.
You just ordered from Myntra. Congrats! You just overpaid. Every Myntra order you place without Buy Hatke Chrome extension.
You would have taken 32. For the 0, like the initial max OR, you can keep a max OR, which is 0, 0, 0, 0, 0. Initially assuming that x is equal to 8 and you did not find any number, or you find the same number that will give the same OR. So you took something like this. Okay. Now what you want is, for the 0, in order to maximize OR, you want to place a 1 over here, right? You want to place it. But what you will do is, you'll start with the root and you will say that, okay, listen, for the 4th index bit, do you have an opposite of 0? It says that no, I don't have an opposite of 0, which is 1. I don't have. I have a 0. You have to take it. You have no other option. So I'm like, okay, if I take a 0, this will never turn on this bit on my number. I'm like, okay, fine. Let's move to the reference. Next, I'll come to the 3rd bit. Now, when I come to the 3rd bit, I say, for this one, do you have an opposite? That's 0. He says, yes, I do have an opposite. So I'll be like, okay, if I take the opposite, this bit will be turned on to 1. I'm like, I'm absolutely okay. Let's take it. And now I'll move to here. Next, I'll come to the 2nd bit. And I'll say, for the 0, do you have the exact opposite, which is 1? He'll be like, yes, I do have. So I'll be like, okay, I can take this. And then thereby this will move to this guy, which is 1. He says across over here. 0th bit. And I say, for the 0, I want the opposite. Yes, I want. So I take it and I go to the last try. So if I take it, this will turn on. So ultimately, if you see, I ended up checking for all the bits. I ended up checking for all the 5 bits. And I eventually turned on the bits which is possible. So if I keep on turning on, I'll end up turning the bits which are possible and I'll get my answer. Don't you think? This is your answer, which is 0, 1, 1, 1, which is nothing but 15. You eventually get your answer. Yes, that is how you do it. Now again, for the question which states, what if 1 did not exist? It is bound to exist, or 0. Kuch to ho gayi, because the number is of 5 bits. So either a 1 will be here or either a 0 has to be there. Like there has to be. If you're following this pattern of try, a try cannot stop here. A try will be of 5 bits. So it will always either have a 0 or a 1 over here. It has to have, because I'm always making sure I take 5 bits. Even if for 7 it was 1, 1, 1, I did not insert 3 bits. I inserted 5 bits exactly. So it's always sure that you will always have all the 5 bits. So even if you do not find a 1, you're bound to find a 0. You're bound to find a 0. You'll either find a 0 or you'll either find a 1, because the try length has to be 5, and that is what we made sure. So in order to solve this problem, in terms of 32 bits, you just have to make sure you insert 32 bits instead of 5 bits, and you have to just transfer the logic from 5 to 32, which I'll show you in code. Now we have solved this particular problem. We're given an array of numbers and a number x. You find the max value of array of I of x. Now the question that we were given was, given array 1, given array 2, do x XOR. So if I ask you, how do you solve this particular problem? It's very simple. Why don't you treat it as the same problem, where I say that, okay, array 1 is what I insert into the try. Okay, array 1 is what I insert into the try. And in order to get x, what I'll do is, x will be nothing but all the elements from array 2. Like once I'll try array 2, from array 2 I'll try the 0 to be x, the first index, and the second index. Similarly, I'll go on my answer. Design a function which gives you the maximum with array of I elements of array 2. So, and now you'll just have a max function, something like get max, where you'll be having an x and this will return the max. So while designing a try, have an insert function, have a get max. And just call this get max for implement this, and then we will move ahead. So the time complexity, insert all the elements of 32 bits into the try. So n into 32 for array 1 insertion.
Debugging. It's one of the most time-consuming and frustrating parts of being a programmer.
Plus, now you have to go across and find the maximum number for every array 2. So it's an m into 32 again, because for all the elements of array 2 you have to find across 32 which is the maximum. But this is what you can do specifically, and you cannot. Let's move on to the coding part. So I hope you have understood the entire explanation. Now it's time to live code it. The C++ code will be on the left and the Java code is on the right, so that the Java users can also follow. And you know what will be over here? A node star of links size 2. That is for sure we will be having links for 2, which one will represent the 0 while the other one will represent the 1, right? Next is we will be having a contains key, where we will be telling him that, hey, listen, this is the bit number or index. Can you tell me this index is set or not? So probably I can keep it as bit rather. Return links of is this bit set or not. Now, how do you check if it is set or not? Can I say if this is not equal to null, then it means it is set, or else it is unset, right? What if I want the next guy? So I can write node.get, and for this bit, can you give its reference node? He'll be like, sure, why not? Let's give him the reference node. So links of bit will be the reference node for this particular bit, correct? Going across, what if the bit doesn't exist? Then I need to put it across. So I will be giving, can you, on this bit, can you put this particular new node? Like you have to just put a new node. So please put it that. So you can say for this particular links, yes, for this particular links on this bit, can you put this reference node? That's how you'll do it. And this is how the node will look like. Now, with respect to node, you need a try. So what you'll do is you'll create a class try. Okay, so please create a try. Now, whenever you create a try, you always know there is something which is known as the root, correct? So please create the root as well. So this is how you'll create the root. Now for this try, there will be a constructor. Now on this constructor, this root will be always initialized to a new node which will be resembling a couple of bits, right? This is how the constructor will look like. Now in this try, you will always have something as a void insert, right? You will always have something as a void insert. So in void insert, what will you be given? You'll be given the integer, which is a 32-bit number, Now if you're given 32-bit number, if you remember the algorithm, we started inserting from the extreme left, that is from the 31st bit. So you start checking from, okay, so on the I set or not particular node and ask, hey, that's okay to create a reference for that guy, because this is as of, why don't you put a new node number? In short, you start from 31st and then go to the next, as simple as it can get. Now you have to write a function. Yes, you have to write a function public, because given, can you please give me the max? Yes, can you please give me the max is what I'm asking you. Now can we do this? Let's see. So we're given a number. If you remember the first question that I discussed, like the first part in order to solve this question was given a number, tell me from that try which is the maximum number you can get. So in order to get that, always remember you need to start with the root. Start. And now you will start right from the back, because you need the maximum possible. So this is where you start, and in order to get the number, probably you can keep the max number equal to 0, correct? And now what you'll do is you'll find the bit over there of that number. So bit equal to, you can say num I and 1. So this will give you the bit. Okay. So once you have got the bit, can I say I need the opposite of it? You remember the XOR concept? I need the opposite of it. Now I will check if node contains the opposite of it. Okay, let's see if the node contains the opposite of it. So in order to see the opposite, it's 1 minus bit, because if it's 1, it's 1 minus 1, 0. If it's 0, it's 1 minus 0, 1. If it does not contains the opposite, yes, I repeat, if it contains or if it does not contains, this will be couple of cases. So there will be couple of cases. If it contains the opposite, then I definitely know that I can make this bit. Yes, I can make this bit as 1. So 1 left shift of I is what you will do, or to add this to your maximum number. Correct? And at the same time you will say, okay, can you please go to that particular guy that is 1 minus bit, and over here also this. Okay, done. Next, if it does not contains, that means you cannot make it 1. It will still stay as 0. So no need to do anything. Just go to the next guy, which is the bit itself, because it's a similar ones. And this is how you will scroll across. And once you have done this particular thing, you can return the max num. So what I can say is, you have designed a function to whom you give a num and defines the maximum from the try. Correct? Now coming to this particular question, this question stated you had an array 1, you have to pick a number from array 1, and then you have to pick a number from array 2. So can I say what I will do is, I will do nothing. Instead I'll just create a try object of this particular class try. Okay, and I'll just iterate across the array 1, and I'll say try, can you please insert, yes, can you please insert the IT guy, like can you please insert this number. He'll be like, okay, I'll insert it. Now once you have inserted, can I keep a max 0? And now can I do an auto of IT on the array 2? Okay, but what help does it give me? The help that it gives me is, I have an entire try ready with all all the array elements number.
We are at the biggest IT hub of India and we are just asking one question: DevOps, cloud, or cybersecurity? Which one is right for you?
So
Please go and see it's all with the store using the insert X, because this can be reused so that you can reuse it like this, making so please make sure it has interviews quotes like the nation. And yes, if the strivers, check out the strivers in case. And yeah, I've started a new to consider subscribe this video. And yeah,
Do you keep on hearing AI is going to take a job? Well, here's the truth. AI won't replace you.
And 1. So this is opposite of it. You remember see the opposite 1 minus. If it contains or if it does not contain, this will be a couple of cases. Then I